All right. If you have a function y equals f of x, common notations for the derivative. So the notation we've used so far is just f prime of x. You may also see if the function is given just as an equation, so y equals, you can also use y prime. So it looks like y to the first power, but it's not. Y prime is how you would say that. And then the other most common notation, so I'd say f prime of x, y prime are very common, and the other that's the most common is dy dx. So these are the most common ones. I'll talk more about dy dx, but I'm going to list other notations you might see. So you might also see df dx. Again, I'll explain what all of these mean. You might see d dx followed by f of x, or capital D followed by f of x, or capital D with a subscript of x followed by f of x. These all mean the derivative of a function with respect to x. So as long as the function is a function of x, these all mean find the derivative of the function with respect to x. This notation here, the dy dx, this is Leibniz notation. Yeah, so Leibniz is the person who invented that notation. It is very common, the Leibniz notation. So from here on out, we'll be using both notations. Yep, Leibniz, Leibniz. I doubt it. Maybe.
Regal notation, and then you'll win like a Peace Prize.
And you might also want to make a note. You heard how I said it, but you say it as dy dx is how that's read, not dy over dx. You just read it as dy dx. But it means the derivative of y with respect to x. So the one that's following it, the df dx, that would just mean the derivative of the function f with respect to x. This here as well, the d dx, this means you're taking the derivative with respect to x of whatever follows, so the derivative with respect to x of the function f of x, and that's also what the capital D means. So on here, the capital D and then d dx, these are called differentiation operators. So it indicates the operation of differentiation. Differentiation is the process of finding the derivative. I know it's a lot of notation and then vocabulary that goes along with it. But anything that follows the capital D, this last one is just more specific, saying the derivative with respect to x. But capital D and then d dx tell you to take the derivative with respect to x of what follows. And like I said, the first three, those are the most common. So you'll see those throughout the rest of this year. Following this then, we're first looking at what it means for a function to be differentiable at a given value or on an interval. So a function f is differentiable at a value a if f prime of a exists. So as long as basically saying a function is differentiable means the derivative exists at either that value or on an interval. If it just says the function is differentiable, that means the derivative exists everywhere on its domain, if it just says it's differentiable. So it's differentiable on an open interval a to b if it's differentiable at every number in the interval. And we typically describe differentiable on an interval as an open interval, so not including the endpoints. And then this, I put theorem in parentheses, I put 4, just because in the book, again, if it references theorem 4 in any practice problems, this is the theorem it's talking about. The theorem itself doesn't have a specific name. But it is an important theorem because it shows the relationship between differentiability, so the derivative existing, as well as continuity that we talked about in 2.4. So it's an extremely important idea or theorem. If f is differentiable at x equals a, then f is continuous at a. So if you know a function is differentiable, say they just tell you f is a differentiable function, then you automatically know because of this theorem that it's also continuous. So differentiability implies continuity is a way to think of it. However, the converse of that statement is not true, well, not always true, I should say. So I have here the following statement is not always true. This would be the converse. If you remember that from geometry, if you flip it around, you cannot say that if a function is continuous, then it's differentiable. So it doesn't go the other way around. You can say if a function is not continuous at a, then it's not differentiable. So that would be, if you remember again from geometry, the kinds are positive. But I'm going to show you why this is not always true, that you can't say if it's continuous, then it's differentiable. I'll show you the example if you have the function absolute value of x. And I'm going to explain this with the graph of this function. So we know this is a v with the vertex at the origin. So where is this function continuous? On what interval or intervals is it continuous? So it's continuous everywhere, negative to positive infinity. There's no breaks in the graph. There's no asymptotes. However, this function is not differentiable everywhere. So on a graph, remember that the derivative represents the slope of a tangent line. Where on this graph would there not be a tangent line? At 0 because of that corner. So because there's a corner, there's no tangent line. And if there's no tangent line, there's no derivative, since the derivative is the slope of the tangent line. So I'll just say here f of x is not differentiable at the x value 0. So even though f is continuous at 0, it's not differentiable at 0. So that's showing that you can't say if a function is continuous, it implies it's differentiable. That's not true. But if you do know that it is differentiable, then we can say it's continuous. So that's what this theorem says. And that'll come up as we kind of move through this course. There's a lot of theorems. One we've already worked with, the intermediate value theorem, where you have to know a function is continuous. So if you're given that a function is differentiable, you know it's continuous. So that's where that is used quite often. So I'm going to look or show you a few different cases where a function is not differentiable. We already know one. If there's going to be a corner in the graph, it's not differentiable. So I'll just show that as number 1. We could have the same graph. But it could be a corner, or it could also be a kink in the graph. So if you see a graph that goes like this, so if there's a corner like we saw in the absolute value function, or they call that a kink in the graph, then there's not a tangent line there. Hopefully that makes sense. There's no way to draw a tangent line at that point. We already taught, or I already referenced another case where it would not be differentiable, and that's, I said the contrapositive of this would always be true. If you know a function is not continuous, then it's not differentiable. So if I had any discontinuous curve, yeah, so it could be a jump. It could just be maybe there was a hole in the graph and it kept going, but still if it's any discontinuity in the graph, the derivative would not exist there. So if there's a discontinuity, it's not differentiable. And then the other case where it would not be differentiable is if there is a vertical tangent line. So if you had a curve that's still a function, but say your a value is here, the tangent line at that a value would be vertical. And vertical lines don't have a slope, or the slope is undefined, and therefore the derivative would be undefined, or there would be no derivative. So if there's a vertical tangent, it is not differentiable at that value. So example 1 is just giving you a graph and saying state with reasons the numbers at which f is not differentiable. So kind of looking at these 3 cases. So where or what's an x value where this function would not be differentiable? At -1. So what's going on at -1? And at 4? And at 8, there's another pink or a corner. Yeah, and the vertical tangent is the one that's either often missed or it's often, I don't know if misinterpreted is the right way to say it. Make sure the reason is that it's a vertical tangent, not a vertical asymptote. A vertical asymptote is different from a vertical tangent. So it's discontinuous at the x value 11 because of the vertical tangent line. But there's no vertical asymptote on the graph of f, so that would not be a valid reason for the for it not being differentiable. Questions right now? Okay, and we had already talked about some of these ideas when we were graphing derivatives. We already talked about how at a corner the derivative doesn't exist because you don't have a tangent line, so it's just giving you a more formal explanation of that. Now we're going to get into the higher derivatives, starting with the second derivative. So f prime of x, the derivative you've been finding, that is the first derivative. So then, if you find the derivative of the derivative, that would be f prime of x prime, or it can be written this way. So it's f, and it looks like 2 little apostrophes there, x. This is read as f double prime. F double prime. And that means the second derivative. The derivative of f prime of x. The way you write this in Leibniz notation, it looks weird. I didn't make it up. So this would be f prime would be the first derivative. That would be the dy dx. And so the second derivative would be taking the derivative of this. So it would be d dx of dy dx. So the derivative with respect to x of dy dx. But the way this is then notated is, I'm going to say it how it looks, although it's not just how you say it. So it looks like d squared y. That's not how you read it, though. Looks like d squared y over dx squared. So if you see this notation, this means the second derivative. The best way I can explain why the 2's are in the places they're in is it's kind of taking the d dx and this d dx, and that's what's being squared for your second derivative, so that's why the squared is here. I know there's not parentheses around this, but to think of that as being in the denominator as well. So the second derivative of y would be the best way I can explain that. But that would be the Leibniz notation for f double prime. And this does come up. Occasionally on the AP test, it'll say find this, so you have to know what this means in order to be able to find it. So in example 2, here's a function f of x, and it says find f double prime. In order to find the second derivative, what do we have to find first? First derivative. You all know how to do that. So in your groups, I want you to find f prime. Once you have it, once everyone has it, I'll have it up here so you can check. You can go ahead then and find the derivative of f prime to find your second derivative.
I thought it was called a
All right. Check what you have. I think you all had f prime, correct? 3x squared minus 1. And then I pointed this out if any of you wrote it. I know a lot of you didn't, which is fine. But just know that if you're finding the second derivative, this is what your limit would look like. It's no longer f of x plus h, but it would be f prime of x plus h, because you're now substituting it into f prime, and then minus f prime of x instead of f of x. So the limit essentially is the same, but if you're writing the formula for f double prime, just make sure that you're including the f prime of x plus h and the f prime of x. But it is 6x for your second derivative. So, well, if it wanted f prime of x, so make sure your variable is x. So you just have to put x in place of a.
So would that be wrong to do this?
Probably. You want to make sure you want to make sure you're using the right whatever variable they specify is the variable you have in your answer. Yeah, you could do that. Yeah. Yes.
Is it considered the road trip?
We're not done yet.
It is. We spend the night until road trip.
All right.
Yeah, 8-hour road trip.
I need your attention. We can get to the road trip later. So, just to discuss quickly here, relationships now, because we have a second derivative, relationships between the function, the first derivative, and the second. So you have f of x. We know f prime of x. What did that represent on the graph again, or what was the main interpretation of f prime? Slope of the tangent line. Or we could say it just represents the slope, I'll put in parentheses, or rate of f of x. It is the slope of the tangent line, but that can also be interpreted as just the slope of the curve itself at a specific point. And then f double prime then is going to be same interpretation, but with reference to f prime. So f double prime is now the slope or the rate of f double prime, or f prime, sorry, of x. That looks messy, hold on. There we go. So some of you have already, I've just heard in conversation when you're talking about a function decreasing and then at a decreasing rate, or increasing at a decreasing rate. When you're adding the decreasing rate or increasing rate at the end, you're describing the second derivative, because then you're describing the rate of the first derivative. So then I have relationships that we've talked about between a function f and the first derivative. So we know when f prime is 0, that's when f has a local max or min or a horizontal tangent. When f prime is greater than 0, so when f prime is positive, that's when f is increasing. And when f prime is negative, that's when f is decreasing. F and f double prime have those same relationships. Dylan, did you have a question? If it's a polynomial. Yeah, because we had talked about that, how with a polynomial, the derivative goes down a degree. Yes. So with polynomials, yes. Not with every curve, but yes, with polynomials. So the second derivative, now if you were given the graph of f prime and asked to graph the second derivative, you're going through that same process that you went through when you were graphing f prime given the graph of f. So f double prime is going to equal 0 when f prime has a local max or min, or in more generally, when f prime has a horizontal tangent. And then f double prime will be positive when f prime is increasing, or when f prime increases. And f double prime will be negative or less than 0 when f prime decreases. So it's those same relationships between f and f prime that we've talked about, but now they're between f prime and f double prime. Because f double prime is still the derivative of f prime. So the graph that I included there, and I know f double prime is kind of hard to see. But it shows you, this was the function on the previous page that we found the derivative and second derivative of. So f is the function from the example you guys just did. I could probably highlight what it. This is f. And then think about those relationships if you were to graph f prime, the derivative of f. It has two horizontal tangents at the local max and the local min. And you can see that's where the graph of f prime crosses the x-axis is at those horizontal tangents. And then where f increases, you can see f prime is positive. Where f decreases, it's negative, and then it increases again, so it's positive again. And you get a parabola. So f was a cubic function. F prime is now a quadratic function. So with polynomials, we did go down that 1 degree. And now from that quadratic, you can see there's one horizontal tangent, and that would actually be at the x value 0, and that's where f double prime passes through 0. And then to the left of that horizontal tangent, f prime is decreasing, so the second derivative is negative, and then after the horizontal tangent to the right, it is increasing. F double prime is positive. But you can see then from a quadratic, the derivative of a quadratic is linear. So it has those same relationships we've talked about. Interpreting this more as, well, going back to our main application in calculus, which is position, velocity. Now we're adding a second derivative to that. So if the original function represents the position of the object, or the displacement, f prime represented the velocity, Those of you in physics probably know what is the second derivative? Acceleration.
Yeah.
The rate of change of velocity is acceleration. So if you are answering questions about acceleration, you are finding the second derivative to do that. So they might there's calculus based physics and then non-calculus based physics. What? No. Right. We apply it can be applied to physics. So physics can use calculus. All right, I need it quiet, please. Yes, question? Can you say that again? Yes, that's what we're going to be looking at the 3 days next week when we start the last part of chapter 2. We look more at that, is using the second derivative to help us figure out stuff about the original function. So you're kind of a step ahead. All right, getting past then second derivatives, higher derivatives, third derivatives. This would be the derivative of f double prime. So if you had f double prime of x and then you took the derivative of that, that is just written now with a third dash and is read as f triple prime. Or you could say the third derivative. So this would represent the slope or rate of f double prime. You can also write, rather than f triple prime here, and I didn't write this for the second one, it would also apply to the second derivative, but you could write that as y triple prime. So you could write y double prime as well. I know I didn't write that before. But then for Leibniz notation, it would look similar to the second derivative, but now you'd see a 3 instead of a 2. So it looks like d cubed y over dx cubed, although it's not how you say it, you would just say the third derivative. But that's how the third derivative is notated with Leibniz notation. And then if you have a derivative higher than 3, these are now notated this way. So rather than continuing to add marks, 3 is the highest you go with marks. After that, for example, well, I'll write this in the general case. So rather than putting the marks, you would put in parentheses the number of the derivative you're finding. So I will put an example for the fourth derivative, but I'm just writing the 3 main notations we have. And then again, note the number n for both the f and then the y, it is in parentheses, so you're not mistaking it for the fourth or the fifth or the sixth power because it's referencing a derivative. So if you had a fourth derivative, you would write it as f and then not to the fourth power but parentheses. It would look like this, or like this for y. So it's not y to the fourth or f to the fourth of x. The parentheses indicate that it's the fourth derivative. And then you would just have the 4's in place of the n's for the Leibniz notation. And that's anything higher than the third derivative would be notated that way. So if it was the seventh derivative, you would see a 7 there. All right, so in example 3, this is continuing from example 2. So we had the original function x cubed minus x. In example 2, you said f prime of x was 3x squared minus 1. And then you found the second derivative, f double prime of x, was 6x. This is now asking us to find the third derivative and the fourth derivative, f triple prime and then the fourth derivative. So here, I could certainly do the limit with 6x to find the third derivative, but I don't need to, because what type of function is the second derivative? It is a line, it's linear, with a slope of what? And if the derivative is the slope, the derivative is just 6. Or you could do that. And then you'll learn. You'll appreciate it more if you don't learn it right now. And then the fourth derivative, what type of function is your third derivative?
0. 0.
This is a constant function. And a constant function has a slope of 0. So then this means any derivative after the third derivative is going to be 0. Yeah, y equals 0 would be the fourth derivative, yeah.
That's cool.
All right, so there is practice for this. I know it's not typed on here. I have it on the board. So these 6 questions would be practice on today's material. Could be on your homework quiz next week.
Is it a road trip?
Next week, Tuesday.
It's not.